Next, it's a very important topic, that is the De Morgan's theorem. So it will be mainly asked to state and prove the De Morgan's theorem. There are two theorems there, De Morgan's first theorem and De Morgan's second theorem. And please look at the notes. The De Morgan's first theorem states that when the OR sum of two variables are inverted, I repeat, when the OR sum of the two variables are inverted and it is same as inverting each variable individually and then ANDing these inverted variables. So I shall tell you. First theorem states that when the OR sum of two variables, the OR sum of two variables is inverted and that is equivalent to inverting the two variables individually and then ANDing them. So this is the first De Morgan's theorem. So this can be written like this: x plus y whole dash. We cannot say x plus y dash because we are having the bar for the whole expression. That is why it is x plus y whole dash, which is equivalent to x dash and y dash. So the De Morgan's first theorem states that when the two variables are ANDed and they are inverted, and that is equivalent to inverting each variable, when the two variables are OR and they are inverted, and that is equivalent to inverting each variable and then ANDing it. We can prove this by our truth table also. We just have to put up a truth table for this equation. So we shall put up a truth table for this expression. As I have told you previously, when we evaluate a boolean expression, we have to see how many variables we have. We have mainly two variables, x and y, and that must be the power of 2. We have two variables and it is 2 to the power of 2. So we will have 4 rows over here. One variable we want is x, then we have y. Each individual terms, x dash we require, then we require y dash, and we require x plus y, then we require x plus y whole dash, and then x dash and y dash. So these are the different terms we require to put in our truth table. These are the possible values for x and y. So x dash, the opposite value of x. If the x value is 0, then x dash is 1. Again, if the x value is 0, then it is 1. If it is 1 here, then it is 0, 1, again it is 0. Now let us take the value of y dash. Y, it is 0 here, then it will become 1. Y, then it is 0, 0, it will become 1, 1, it becomes 0. So this was x dash and y dash how we took. Later now, x plus y. X plus y. 0 plus 0 is 0. 0 plus 1 is 1. 0, 1 plus 0, 1. 1 plus 1 is nothing but 1 again. Next, x plus y whole dash. It means this value's complement. Complement of x plus y. 0, 1, because it complement of this term only. 1 becomes 0, 1 becomes 0, 1 and it becomes 0. Next we have to add the x dash value and y dash value must be ANDed. 1 and 1 is 1. 0, 1 and 0, and I told you both the value must be there, or 3 or any number of variables, but all the variables must be true, only then the value will be true. If 1 is going false, then the whole result will be false. 0, 0, 1, ANDing 0, 0 and 0, nothing but 0. Please look at this point now. X plus y whole dash, x dash into y dash. The two columns here are equivalent. So we have proved the first De Morgan's theorem using the truth table. This is how we prove the De Morgan's theorem using the truth table. You just have to look at, don't worry about the statement there. You just have to remember the equation. The theorem states that OR of two variables are inverted, that is equivalent to inverting each variable and then ANDing. When the OR sum of two variables, if it is inverted, and that is same as inverting each variable and then ANDing it. So we have proved this since these two columns are identical, and we have proved it using the truth table, and we can also prove this using algebraically. So when we are proving this algebraically, we will have to have all the laws thorough. That is, first we make use of the complementary law. The complementary law says that a plus a dash is equal to 1 and a into a dash is equal to 0. A variable is ORed with its complement will give you the resultant value 1. A variable which is ANDed with its complement which will give you the resultant to be 0. So if we let us take a value to be x plus y. We are taking x plus y as a single term plus this complement. This is a variable. We shall consider x plus y is a single variable. Its complement is nothing but x dash into y dash. We have changed the symbol, just that we have changed the symbol. X plus y's complement is x dash into y dash. We have used a symbol OR over here, and then therefore the value will be equal to 1 according to this. So here what is happening? This is a plus a dash, because it is opposite of it. X is complemented, the plus is complemented, again the y is complemented. So x plus y's complement is x dash dot y dash, that is nothing but a plus a dash. A plus a dash will always be equivalent to 1. Equivalent to 1. The same way we will have x plus y and x dash and y dash. Since we have a and a dash is equal to 0, this variable is and its complemented are ANDed, and it will give the value 0. So these two must hold true if this theorem is holding true. So after this we shall prove it. We shall see the proof of the first part. We have x plus y plus x dash into y. So we will have to multiply this term with x and this term again with y. So we should have x plus y into x dash now y dash is multiplied with x plus y I hope you understood. X plus y plus x dash, x plus y plus y dash, because it is a multiplication here symbol or it's a dot operator here, we will have to use a dot operator in between. This part is been added to this one with the plus, because it is here we cannot simply multiply like that. There are some mathematical rules to be multiplied also. X plus y will be added with this also, and x plus y has been added with y plus dash also. So what happens next here? X plus x dash, x plus x dash plus y and x plus y dash. These two terms we have here. X plus x dash is nothing but 1 plus y. Y plus y dash is nothing but 1, that is x plus 1. We already know 1 plus y or 1 plus z or 1 plus x is nothing but 1 into x plus 1 or y plus 1 or z plus 1 is nothing but 1, and that is equal to 1 into 1 is nothing but 1, and which is our RHS. I hope you understand. X plus y plus x into y we have. This is like a plus b plus xy. You simply cannot have just multiply this because there is a plus symbol in between. We will have to take a plus b plus x into a plus b plus y. This is how it holds. The same way we are putting in like this, x plus y plus x dash, one of the terms, into x plus y, that is nothing but ab, a plus b into the y dash. Then here we are combining for the sake of our theorem. So this was proving the first part of De Morgan's first theorem. Next we shall prove the second part. Second part says that x plus y into x dash and y dash, when you multiply, see a and a dash must give you the answer 0. A variable ANDed with its complement will give you the value 0. So here we have multiplication in between. So what happens there is x, this term must be multiplied with this whole term. Again this term is multiplied with this whole term and it is added in between. X into x dash into y dash plus y into x dash and y dash. So this is the basic algebraic equation how we solve. Here if we are having a plus b and it is multiplied with c d, we will have a c d plus b c d. The same way we are multiplying these also, x plus y into x dash and y dash. We are taking x with the whole term, x dash into y dash, y with the whole term, x dash into y dash. So we know x into x dash, x into x dash, that is a into a dash will correspond to 0. So 0 into y dash plus again we have y into y dash. Y into y dash will also correspond to 0 into x dash. So anything which is ANDing with 0 will give the value to be 0, plus 0 and x dash also will give you the value 0, and that will result in the value 0, and which is nothing but our RHS. So we have proved the two parts of the De Morgan's first theorem. Now we shall get into the De Morgan's second theorem. What does the De Morgan's second theorem say? So the De Morgan's second theorem states that when the AND product of the two variables is inverted, and this is same as inverting each variable and then ORing it. So what was the first De Morgan's theorem saying was, when the OR sum of two variables is inverted, and that is equivalent to OR sum of two variables is inverted, and if each variable is inverted and ANDing is same. The De Morgan's second theorem states that the AND product, not the OR sum, it's the AND product is inverted, it is equivalent to inverting each variable and ORing it. So we have already proved this one. This is the De Morgan's first theorem and this one is the second one. Now we will have to prove this one. So please look at the notes over there. We can prove the second De Morgan's theorem using the truth table. So this is the second De Morgan's theorem. X, the AND product is inverted and it is equivalent to inverting each product and ORing it. Each variable is inverted and it is ORed. So we shall have the truth table proof first. We have two variables. Two variables means 2 to the power of 2, which is equal to 4. We will have to have 4 rows. So 4 rows we should have, and what are the columns we need to have? First we need to have an x column, an y column, an x dash and y dash, x into y whole dash, x dash plus y dash. So these are the terms we need to have, and now we shall put in the possible values. So these are the possible values of x and the possible values of y. We have x dash. X dash is 0's opposite. 0 will be taken to be as 1. 0, 1, 1 taken to be 0 because it is complementing. 1, it is 0. Y dash, 0 becomes 1, 1 becomes 0, 0 again it becomes 1, 1, is 0. So, we got the value for x dash and we got the value for y dash. Next we have x and y. X and y. 0 and 0 is 0. 0 and 1 is also 0, or you can simply consider, this is a small trick for you, and is always multiplication. 0 into 1. Anything which is multiplied by 0 is always going to be 0. 0 into 1 is 0, 1 into 0, 0, 1 into 1 is 1. Now, x and y's inverted value. Whatever the value we have here, that must be just inverted. 0 becomes 1, 0, it becomes 1, 0, it becomes 1, 1, it goes to 0. After that, we have x dash plus y dash, that is x dash or y dash. We have to consider only these two columns. These two columns must be considered and these must be odd. 1 or 1, 1. 1 or 0, 1. Because ORing, if one value is true, then the resultant is true. 0 or 1, that is 1. 0 or 0 is 0. Please observe over here, we have x into y whole dash, x dash plus y dash. These two columns are identical. So, we are proving the De Morgan's second theorem using the truth table. This is the proof by truth table. Usually they will be asking only for the proof with the truth table, but if at all they ask for the algebraic proof, then you will have to prove what is given in the notes over there. Next, we shall prove it algebraically. The same way as we took the theorem a into a dash is equal to 0 or a plus a dash is equal to 1. The same way here also we are taking the same. Like, see, x into y, it's a variable xy, its complement is being odd and that will be equal to 1. And x into y, this is the same variable, it has been ANDed, its complement, when it is ANDed, the value will be 0. So, here we will have to prove these two. This is the proving of part 1 and this is the proving of part 2. Now we will see how do we prove those. So, we shall get into the first part of the proof. We shall take the LHS, x and y plus x dash plus y dash. We shall only take the LHS and we will have to arrive at an answer 1. Next, x into y, here it is x plus y, but here we have a plus symbol. So, we cannot simply multiply that, but what we will have to do is, we will have to take x plus y plus x into. So, x plus x plus this one and y plus this one, but here in the middle it must be plus. So, x plus x dash plus y dash into, because it is an and here. Here, since it is and here, in between we will have to take a and symbol. Then again y plus x dash plus y dash. So, we know x plus x dash is nothing but 1 plus y dash. Then we have y plus y dash corresponding to 1, 1 plus x dash. 1 plus the variable is always equivalent to 1 and 1 plus the variable is always equivalent to 1 and that is equal to 1 and 1 is nothing but 1, which is our RHS. So, the first part of the De Morgan's second theorem is proved. Now, the second part. Second part same, x into y into x dash plus y dash must be equal to 0, because it is and here it must be 0. So, the same, since it is and over here, we will have to multiply this whole term with this one, this whole term with this one. So, it is x into y into x dash plus x into y into y dash. Okay. The only difference here it was plus. Okay. Fine. Next, we have taken the only difference here is that here we are we are having the or sum over here. Here we are having the and products. Next, x into x dash is nothing but 0, 0 into y plus y into y dash is 0. So, x into 0, 0 and y is nothing but 0 plus x and 0 is 0, which is corresponding to 0, which is our RHS. So, this is the proof for the second theorem, and this is the second part. Always remember, a variable, if it is ANDed with its own complement, will be equal to 0. A variable, it is odd with its own complement, that will be equal to 1. So, what the De Morgan's theorem mainly means is that we have to break the line and change the sign. So, this is demorganizing a expression. Break the line and change the sign. This is De Morgan's first theorem, x plus y whole dash is equal to, as I told you, break the line, change the sign. We have to break this line, that is x dash and y dash, change the sign. Sign is plus and make it and. This is the De Morgan's first theorem. So, what does the De Morgan's theorem say? The same way, x into y whole dash, we just have to break this line and change the sign, x dash plus y dash. So, we have seen the two theorems of De Morgan's, which is very, very important, and we have seen both the proof. One is by proving through truth tables and one is proving algebraically. So, you can see the process. Although the identities above represent the De Morgan's theorem, the transformation is more easily performed by just these steps, by changing the or sign to the and sign and by changing the complementing each of, not just changing, it is just complementing the variable. The variables are complemented and the signs are also complemented, and this process of changing the signs and complementing the variables are called as demorganization. The process in which the complement, the entire function is complemented, the sign is changed and the each variables are complemented, and such process is called as demorganization. I have highlighted the line for you. Break the line and change the sign to demorganize a boolean expression. This is the theorem is mainly used to simplify the boolean expression. There is a big expression and we want to cut it short into small, then we will demorganize it. So, where is this demorganization theorem or the De Morgan's theorems are used? The applications. It is used in simplification of boolean expression. As we did now, we can simplify the whole the expression into one. It is just simplified to just a number 1. Then this De Morgan's law applies to text searching also. Suppose if you want to search for two words, cars and trucks. So if we are just giving for searching the items there in a big list of documents, if you want to search for two words, cars and trucks, then what happens, wherever the cars and trucks are there, both are there, it will return that much document. So Boolean algebra is not a topic to be which is to be neglected. It has to be taken quite importantly because it is used in most of the places. It is useful in implementation of the basic gates operation with the alternative gates. If you want to learn the next chapter in the PU curriculum, that is your logic gates. So if you want to know the logic gates properly, and this is the basic for all those logic gates. Okay, thank you.